Thank you all. Thank you, the organizers, first of all, for inviting me for this. I gave a talk on a new paper that will come out soon on Orionis. And for this talk, I'd also like to thank my collaborators who have been crucial in finishing this project. I'll probably skip this slide because Agnes gave a very nice review already about FEOR type objects. And in this talk, I specifically will talk about FEORINs, the archetype. And this is a part of an ongoing research project at Concoli Observatory. I'm working on eruptive stars on the VLTI, which I joined relatively recently. FEORINs itself, the first eruption was about 1936. It went up by about 6 magnitudes in B. And this happened, of course, in all bands. We see the evolution slowly fading since then, both in the optical and the mid-infrared. For those that are not familiar with the object, it has a rather large reflection nebula here. And if we look closer at it, in polarimetry, in scattered light, in the J and H bands, you start seeing some interesting features, like an arc-like structure here on the east, certain kinds of clumps and streams, and potentially a streamer being located on the west side of the target. And here you can't really see the star because it's hidden behind the chronograph, but the clump you see right here, A, and this one here is a companion star called FEORINS South. Now, FEORINS is also a favorite target for interferometry. And so in the past, people are looking at it in the near infrared, mid-infrared, radio. So there's lots of reports already. An interesting point I wanted to make here is like for every different study, you get different measurements for the size of the geometric properties of the disk, a different inclination and a different position angle for the minor axis. So it's interesting to see whether this can be a cause of perhaps a disk misalignment, or if you have any changes in the disk. We also wanted to check whether you have any change in the SED over time and you have any change in the accretion rates. We also wanted to check whether, looking at the previous image where you have the streamer, if you have any influence by it close to the star, or if you see any changes in the inner disk radius over time. And for this reason, we used MATISSe. There'll be a dedicated talk later on in the conference, but there's also lots of other results with this instrument. Just briefly summarize that this is the new imaging instrument at the VLTI. We have all 4 telescopes, and we get 6 baselines, and you can do simultaneous observations in L, M, and N bands. And it can go rather deep down to a correlated flux of about 0.1 Jansky. Now, for FEORINS itself, this is observations on GTO time, and we have multiple epochs, and it was more of a feasibility study for MATISSe, if you can actually observe this target. I'm not going to show you any images because these were taken in snapshot modes, and we have combination of baselines with the UTs and the smaller telescope with the 80s. Now, the surprising thing here was like FEORINS, the disk itself, or the emitting region, in L and M is rather small. It was marginally resolved in all bands. And we're estimating a size smaller than 2 milliarc seconds, or in L, and smaller than 5 milliarc seconds in N. And just to show you a few of our results. So that on the left, we have the visibilities and the correlated flux, the visibilities and the closure phases. That you see that they're non-zero and probably related to an asymmetric structure. And here we have the L band, and on the right is the N band data, where you can see the silicate feature that is in emission. And because these are snapshot observations, you can have an image to properly see the target. We have to use models. And we started with an analytical model, which is like a steady state accretion disk model, is optically thick and geometrically thin. And for this, we had to fit the current SED, which is collected. You see that this object is fading. So we collected data in the last 2 years from the optical to the mid-infrared. And we explored 2 different geometries. First, the ALMA geometry from a previous paper. And the second was a geometry derived by the MATISSe observations, which had rather large errors because, as I said, the disk is marginally resolved. And we tested those 2 geometries and see the different inclinations, different position angles. And for the first model, in the analytical model, we only fit the hot inner disk. So the results from that one will be fed into a radiative transfer model because the analytical doesn't treat the dust. And for the RAD-EMC 3D model, we had 2 components, the hot inner disk, and the dusty passive disk. Now, these components were both in a way connected to each other, so they don't have any disk gaps or any other strange morphologies. As you see here, 2 plots on the right is the density and the temperature, and we set the barrier at 0.3 AU, which is rather small compared to findings from different studies. And we find that, I'll just show you in a bit, that the ALMA orientation is actually favored when you run the models. And here I have the results from the models. On the left, you have a comparison of the correlative fluxes between the UT observations and the AT observations. On the middle, we have the closure phases, and you see that the difference between the 2 inclinations at the top, the dotted one is the MATISSe geometric shape. The other line is the ALMA model. So it kind of fits a bit better in both, in all correlated fluxes, closure phases, as well as with the SED. Now, since we also have N-band data, we can also look at mineralogy and compare to previous results with MIDI. On the left is the results from a paper by Quantz et al. From 2006. We had MIDI observations 16 years ago, where they looked at what kind of silicate feature you see in FEORions. It's a rather flat-topped spectrum, which means that you're looking at a kind of a larger sized grains, more than larger than 1 micron. When we compare them to MATISSe, we don't really see significant changes between the 2 observations. So overall, roughly 20 years, not much has changed. Apart from a small decline in the flux, everything else seems to be consistent. We still have a flat top profile. We're still looking at rather large sized grains. And we also cannot define whether we have any crystallines or not. There's also a lot of talk about whether you have a 3rd companion. So there is FEORi South, which is further away and it's outside the field of view of these observations. Whether there's another companion, what might be influencing those outbursts. And from the data that we have, we can't really tell. I have some examples here where we ran a couple of comparisons where you have the disk signal and what if you introduce tertiary companion to it. Unfortunately, with the N-band data, we cannot detect a companion within 25 milliarc seconds, which was a suggestion by previous papers from H and K observations with IOTA and the VLTI. But we can exclude, at least in any companion between 20 and 100 milliarc seconds from the star, because MATISSe has the feasibility to find these companions, but here we don't see any signal from that one. We also, if you have a companion that if it was, let's say, some kind of clump, we also don't see that as well. And let me finish with my conclusion. So these are the first results we have from the archetype of FEORions with MATISSe observations. We found that the disk is quite small, is marginally resolved. As Agnes mentioned earlier, these disks tend to be quite smaller in size. The meeting region, we find that the outer radius for the inner, the hot disk is about 0.3 AU. We don't see any significant change in the silicate feature in the last 15 to 16 years. We see that the signal is from larger grains, so larger than 1 micron, and we don't find any crystallines. We also see that from the models, we favor the orientation by ALMA imaging, but we can't really constrain any disk misalignments from this data alone. We cannot detect any companion inside 25 milliarc seconds in the end band, but we can exclude in L, so in the parameter disk area space between 20 to 100 milliarc seconds. And the model, of course, is not perfect, but it could be improved with further observations, because we don't take into account whether there is a change in the boundary, where there is a small gap or some other geometrical change, or even misaligned disk, because in the L band is marginally dissolved, so we can't really tell what's going on in the center of the accretion disk. But we think that with new data we recovered recently with gravity, we might get some idea of what's going on there. And this one is not exactly, because it's so small in size, not an ideal target for MATISSe imaging, but we have other projects in the pipeline. Hopefully, let's look out for those results soon. Thank you very much.
Thank you, Foteini. Any questions for Foteini?
Okay, thanks for that nice talk. When you showed the visibility and closure phase data, you highlighted the non-zero closure phases. Do you know what it is in your models that gives rise to the non-zero closure phases? What particular geometric aspect of the models gives you the asymmetric structure?
We think it's the inclination. When you have a disk which is more pole on or edge on, and that's what we show with the two, the one here in the middle. The line with MATISSe, it's a more disk is more edge on, while the geometry of ALMA is a more pole on disk.
Okay, I mean, I'm slightly confused. Maybe I can follow it up later in terms of if it's still a centrosymmetric image, then the inclination I would have naively thought wouldn't lead to any non-zero closure phases. But anyway, maybe we can talk after. Thanks.
Hi, thanks for a great talk. I was just wondering if you could comment on whether you think the streamers that you see at larger scales are related to the dynamics of the two sources, and whether you think that could be creating the outbursts we see in these kinds of objects. I know you can't investigate that directly with the infrared data, but do you have any plans to look at this with ALMA, or is this something you're thinking about? Just wondering.
Sorry, could you repeat it? But I couldn't hear all of it.
Oh, okay, sorry. Yeah, I was just wondering, do you have any plans to follow up the study of the streamer specifically, and how that relates to the binarity of the system, and how that could in turn be linked to the outbursts that we are seeing? Well, we've been trying to get some sphere data for a while, but we haven't been successful to get the time. Okay. So maybe in the future we'll be more successful. Great, thank you.
Hi, Claire. Thanks for the very nice talk. I was wondering, because this object is a binary, so you have this accretion streamer that could maybe also due to the flyby, like in Z-Canis majoris. And the previous talk was on the binary target. I was wondering how much binarity does play a role in this a priori outburst, and yeah, can we say maybe that all these outbursts are due to binarity, or is there any other mechanism?
I don't know for this one, because this one is they're far away from each other, and there seem to be quite well. Let me think. And the only other study I've seen was from ALMA, where you have a circumbinary material around this and CO gas. But I don't see any interaction from the paper. I didn't see any interaction between the two disks themselves. But if the one is influencing the other.
We have also one question from the chat. Karin says, thank you for this nice talk. I have a question on slide 10. It seems that the fit of the MATISSe closure phases is worse for the MATISSe model than for the ALMA one. Can you go back on this plot, please?
I think it's this one, right?
Yeah, visualize that. This one. Yeah.
Yes, it is worse. Which is why I said that we opted for the ALMA orientation.
Yeah. Any more questions? One last one I want to, are you also planning maybe to look at the gas content of the disk? Because for example, there's some gravity data and there is rocket gamma, there's CO. And maybe you could see for different epochs, the variations in the CO, for example, to get some information on the disk.
So we just got the data a few months ago and they're still going through the whole process of reduction and understanding what's going on.
Okay. Yeah, so if there are no further questions, we can thank Foteini again.
Thank you.